So is AI ready? I would say no. Why? What went wrong in the AI system? First, it solved the perception pillar, which is detecting all the objects of interest, detecting humans, vehicle, drivable area, and for decades we thought that this is the bottleneck. We thought that this is the real challenge of autonomous vehicle. How can you ensure 100% accuracy? It turns out that you can still do this 100% perfectly, and then decide on what should be your next action. How should you move the car? And that's the goal of the planning. The planning, thanks to the perception, will say, okay, I see a drivable area, it's all safe, just go to the crossing. Yet such decision is wrong. And what's the solution? I claim that we must introduce an additional pillar, a forecasting one, in charge of predicting the future state of all social agents up to several seconds. Therefore, we will be able to update our planning and, in this case, decide to stop and avoid a collision. You can tell me, let's be conservative. Whenever I see a pedestrian or something a bit sensitive, let's brake. And indeed, if you apply this rule, especially in my hometown, this will be even worse. 98% of the accidents, thanks to this I can move, are not the example that I show you, but they are because of the AI being too conservative. The AI decide to brake, but we humans, or the drivers, are not able to anticipate the behavior of the AI, and we crash into the car. Again, what's missing, I claim that AI must forecast agent-agent interaction, social forecasting. For me, an agent is any moving entity. It can be another vehicle, another pedestrian, another bicycle, another animal, anything that moves. Let's look at another cool autonomous vehicle, our little robot moving in Lausanne. Again, when it's not crowded, the robot is quite successful in navigating among us. Then, when it's quite crowded, the robot decides to freeze. And it's a very, very popular problem in robotics. It's called the freezing problem. And again, it's because the AI was not able to understand social convention, how we interact in a crowded environment so that we can coexist in a safe manner. Let's look again at the pillars of our AI system for our robot. Again, the perception detects everyone. The planning detects 3 possible paths that are physically possible to move around. Yet, these 2 people are talking to each other. We should not decide to take that path. And that person on the left is moving, and very likely we should take the path on the right to avoid a collision. And that's what social forecasting will do. And if you combine it with the other pillars, it will pave the way to a new type of cognition I refer to as socially aware AI. So let's look at how we can now rethink perception because of our social forecasting. Because we agreed that social forecasting is useful, can we use the current pillars, the current perception pillar? And my answer is no. We need to, again, rethink perception. How? Until now, we thought that putting a bounding box is good enough. And all the perception stack of self-driving car really try to solve this. I claim that if you want to better predict the future, you need to understand the body language. You need to understand the body pose. You need to understand the state of the agent. Are they walking? Are they standing? Are they maybe on their phone? And relationship. Who is interacting with who? In this case, these 2 people were talking, so I knew that it was not a socially accepted path to go between these 2 people. And thanks to this new representation of the body pose, you can still solve the classics, such as detecting humans in 3D, But you can do it with a single camera now. We showed that given only a monocular camera, you can do 3D perception by modeling the uncertainty into the distribution of your height. These numbers are the distance that we detect to the cameras thanks to only an image, without a LiDAR, without expensive sensors. You can do jointly detection and tracking. You can basically detect all these cars, and you see that now the cars do not have a bounding box, but they have all these semantic key points that have a semantic meaning. This is the left wheel, the right wheel, this is the left shoulders, right shoulders, and so on. And we can extract very detailed information. You saw maybe before, but if you look at the face, we are able also to detect many, many key points on the face that we think will also convey information on your intention. What you will do next has also a lot to do with where you're looking at. What you are holding, for instance. We also want to be able to understand if you have a stroller cart, if you have a bag, if you're on an iPhone, if you do eye contact. This is an illustration of eye contact. Eye contact means that, again, you're communicating a signal that first you're aware of me or my AI, and maybe you have the intention to interact with me or go somewhere. Thanks to this, you can now do the prediction of crossing and not crossing. We can, as showed in the first example, then predict if pedestrian will cross, and potentially early enough so that it's a more efficient solution. So we have been promoting this for many years, but a lot of people ask me, how do you compete with industry? I'm like, well, in academia, we can take risks, we don't have any constraint on the business plan, and we can try to be creative. And in this example, it worked because recently, in February 2022, some of the key players acknowledged that key point is the way to go, that semantic key point is the way to go, and we should, for instance, now detect humans as body key point. So 1-0 for academia. Now that I've shared with you how we can rethink perception, let's talk about social forecasting, which is really what was missing in the industry. And even now, some companies are not really doing it. So the way we formulate the problem is given us several sequences of perceived state, and I use several sequences. It's not a single sequence. Each agent has its own sequence. It's different from NLP, it's different from other sequence modeling where you only have one sequence. Here, the exciting part is that you need to jointly model agent-agent interaction. You need to predict the behavior of multiple sequences that have correlation with each other. The way I'm going to interact depends on how the person in front of me behave. And I need to jointly reason on this time series or sequence modeling. And the exciting part is that I do want to be able to disentangle the physics with social cues. There are behaviors that are driven by physics, and others that are driven by experience, by culture, by where I live, and so on. And for the state, the simplest state is the XY coordinate of humans, of agents, of vehicles, whatever you want. But then you can, again, thanks to the perception, be a bit smarter. You can start to use body pose. You can start to use all these additional cues that I shared with you in the perception and try to use this to solve the prediction. In the context of vehicle, you add the scene infrastructure because obviously your infrastructure has a lot to do with your decisions. And how can you jointly model agent, and agent scene? Then, finally, you want to do this in a robust way. You want to be able to predict something that is realistic, that is physically possible. We don't claim that we'll be able to predict everything, and we don't even want to do that because we humans are not able to do it. We have free will, and we have the luxury to decide to do whatever we want. But it turns out that even if we have free will, we are able to coexist and make decisions together in a safe manner. So can we develop the same cognition in AI to still be able to coexist in a safe manner without necessarily requiring a perfect prediction? So over the years, it all started in the 90s, maybe even better, but there was a very key paper in the 90s called Social Force that was modeling pedestrian based on some handcrafted rules, some of our intuition, inspired by the physics, modeling agent as forces, as particles that have forces. And then the community shared other key methodology using, for instance, discrete choice modeling to model pedestrian in 2005, and many others methods over the past decades. In 2014, we started to collect one of the largest data sets on pedestrian interaction. All these models were not necessarily requiring a huge amount of data set. But as you would expect, if you want to then do data-driven, you need data. And we were lucky, thanks to our collaboration with SBB, to put sensors in train stations and collect millions of trajectories on commuters, how pedestrian humans are using a train station. And thanks to this data, now we can rethink this problem with data-driven method. We introduced, to the best of our knowledge, the first deep learning method to model human-human interaction, referred to as social LSTM. And then the community also shared many other methods doing human prediction based on neural network. At one point, we decided to create a challenge, TrajNet++ challenge, so that we can better compare these methods. One issue when you try to compare methods to do trajectory prediction, even if you have the same data, the way you sample your data, your trajectory, has a huge impact. Statistically, we humans are extremely linear. We walk in a straight manner. The key challenging moment is only when we try to interact and avoid each other. So if I have collected data on pedestrian and I randomly sample 2 seconds and try to predict 4 seconds, I will very likely not be able to compare between different methods if I don't share the training and the testing of this sample. And in fact, maybe I need to only focus on non-linear interaction. I don't care about the linear ones. So I should rethink my sampling. And unfortunately, we also and our colleagues did not pay attention to this problem, and we discovered quite late, and that's why we decided to then share a unified benchmark so that we can deal with this problem. And recently, we also discovered that data has a lot of issue, data-driven method. I'm going to share more, and decided to look at how we can inject or take the best of both worlds, the best of data and knowledge-driven method. So let's see what we did. So the current, or the, I would say, most common paradigm nowadays is a deep learning paradigm where you have your observation. For clarity, and I'm using only the XY coordinate of humans, their past coordinates. And we want to predict the future. We can use an encoder, decoder, neural network, learn a latent representation, and solve the task. It turns out that this is not robust. If you take the state-of-the-art method in our benchmark and modify the position of humans in a smart way, you will end up finding one type of interaction that will predict a collision. Why? Well, because our training data is highly imbalanced. What we observe, even if it's millions of examples, are some specific type of interaction, but not necessarily all type of interactions. We cannot claim that we were able to observe all possible diversity, all possible critical interactions. Because again, it's not a matter of how many humans I'm actually looking at, it's the matter of how many critical events and challenging interaction I'm actually looking at. And the solution is, look, let's maybe use knowledge. We know that there are some interactions that we don't necessarily need to collect data because we know the physics. So can we rethink the current paradigm, which is use data to learn the tasks of navigation from scratch? And I don't care about my knowledge on the task. Or can I use data to only learn concepts that I struggle to explain? When we're doing image classification, we were struggling to explain everything. We were not able to tell you how to recognize an image, and using a fully data-driven method makes sense. But for navigation, it turns out that we can explain a lot. For instance, I can start to use a model that is based on the physics. I can, for instance, say that, okay, first, when I see someone, I know that the person will follow the physical law and will very likely continue to keep the same velocity. He cannot jump, he cannot appear somewhere else. So let me not learn the basics of navigation. Let me use a knowledge-driven method. But then I can say, I know, for instance, the distribution of possible output, but I don't know which one is socially accepted. Can I just learn the residual to add to my physical model, to my output that is coming from a physical knowledge-driven method? And that, I can use my data. I can constrain it. I can make sure that it's in a physical range, because a residual, I can always write it as, let me predict an offset from 0 to 1 and scale it in my region, and be able to take advantage of both worlds. I can rethink also my model within the formulation of learning a latent representation. When we do deep learning, we can learn disentangled representation. We can say, can I disentangle, for instance, physical law with social cues? Can I then use this to generalize and do transfer learning? What it means is that I know that the physical law are the same everywhere, but I know that the social rules will change between cities. So all I will have to do is to only update and learn the parameters of my social rules when I go to a new city. Again, I will not need to learn from scratch everything, and then I will be able to use very limited number of examples. I can use knowledge as a supervision, or I can even use more cues on modeling my social understanding. For instance, when we were doing discrete choice modeling to understand or predict human social interaction, this was our output space, discrete positions. And the goal was to be able to predict which of these positions we will basically use or decide to use, which choice in the spatial distribution. To do that, you need to write your utility function and come up with some functions that are according to your understanding of the task. They are attractive functions, like I like to follow someone, I like to follow a goal. There are repulsive functions that I like to avoid each other's. And you can come up with them and try to learn them. And we can learn them also from the data, but we can add an additional term, which is other cues that we don't know how to model, we don't know how to write a function, we don't know if we missed something, but we give the opportunity to learn it. And it can even be different signal. It can be an image. It can be any input that we want. And then we can have an interpretable model, understand the correlation between our input and output, and share some intuition of why we are predicting what we are showing. We can, in this representation that is discrete, we can again add this residual that I told you before, so that we make the discrete output continuous, and we can use again a neural network to add this residual. Another strategy to use knowledge is, can I basically rethink my supervision? Many of the successful results of deep learning were supervised learning. And what I like with supervised learning is that I'm teaching what is correct and what is not. It's the principle, the opposite principle. Maybe knowledge is obtained by understanding the opposite of what you try to do. And this is something I really like. And it has shown success in machine learning. The basic of machine learning is you collect positive, negatives, and you train, and you're able to solve the task. In our case, we only have positive. But can I rethink them by also modeling negatives? And the answer is yes. There are behaviors that I know that are physically not possible. So I can artificially generate them and use them as negative. I said, okay, try to classify a correct behavior with a negative one, and my negative one is artificially generated. And by doing that, I add an extra supervision, and the model becomes much more robust to even all these outliers, all these critical events that I did not observe in my data. I am able to simulate critical event. Let's do it, and let's take advantage of that. The last issue is distributional shift. I know that when I collect data from a city and test it in a different city, I do have some shift in the domain. I should be able to be robust to that. And one way is, again, to see if we can do test time adaptation. Like, given our disentangled representation, can I update it given some samples of my new domain, not many, at test time, so that I am more robust to my model. So this was on the methodology. I think I have 1 minute to share what we have done on the evaluation. I'm going to go a bit fast. One thing that we noticed, I told you our data-driven method were not robust, and it's because of this issue. We noticed that if we perturb a bit the input, few centimeters, which are realistic because our sensors are not that precise anyway, we are able to find a set of perturbation that will lead to a catastrophic outcome, a collision. And we took all these state-of-the-art method. We look at the original collision rate, which are still non-zero, which is bad. We want this to be 0. And then we looked at if we are able to find an adversarial realistic example that will lead to a collision. And indeed, we were almost always able to find perturbation that will make this model have huge number of collisions, which is not acceptable. And by doing that, we can then use this to augment our training. And the first result that we obtained, we went from 7% collision rate to 6%. It's not good enough. We need to do more. But this is something to be aware that our current evaluation metric needs to also think about this type of problem. We also did it with respect to the vehicles. We took state-of-the-art model, we took the scenes, and we started to change the scene infrastructure. We can do that. We know that you can create turns. They are realistic, they exist, and we can see if the models will go off-road. It turns out that all the state-of-the-art models from the industry, from the research lab that are competing on the benchmark, public benchmark, from Google, from all the big players, are not robust at all. Here is the distribution of off-road. This means that the model was basically going off-road when the scene had this type of curvature. And the exciting thing is that then we can check if this scene that we generated artificially exists, so that we can give a feedback that, look, your model is not robust, and it will not be robust in, for instance, Paris. Thanks to our artificially generated scene, modified scene, we are able to retrieve a similar scene and communicate that you don't need to go collect data in all the world. I can already tell you, if you give me a model, where your model will fail, in which street, so please make it more robust. And this is an example you don't see, but there is an observation, and the prediction goes straight in the wall, which is not acceptable. We can do that with many scenes, and we have quantitative number. Again, how robust they are. They are not robust, and we need to address them. So I'm going to stop here. Sorry for the extra time. I'm going to, again, remind you the 3 pillars. Thanking you. Please go visit the lake. It's beautiful, and everything we have done is open source. You can go on this link and download all the codes that is available.
Thank you, Alex. I suppose we have time for a couple of quick questions through this inspiring talk with a lot of visuals.
Yeah, thank you very much for your talk. I was wondering, are you in touch with the industry, or are you aware of to what extent, let's say, Tesla and Waymo are either adopting this or, working on their own similar solutions? And also, maybe based on that, how optimistic are you that these players are solving self-driving in the next couple of years?
So the head of Tesla, self-driving car, is coming next week to our lab to talk to our students, because we're teaching deep learning for autonomous vehicle. So Andrei Karpathy is coming here. So yes, obviously all the key players in the industry are our friends. We collaborate. We argue with each other. But it would have not been possible without any collaboration with industry. They are fantastic to collect data. So we decided to not worry about data. They are providing the data. So it's a really collective work. And your next question is, how optimistic am I? No, what was the?
Yeah, how optimistic are you that self-driving is going to be solved in the next couple of years?
Well, first, it's already there. I mean, I drove 3 hours in autonomous mode this weekend on the highway, but it's not everywhere yet. Honda, for instance, our partner, is the first car manufacturer commercialized level 3 and being allowed to do it. So it's not a matter of will it happen or not. It's already happening, but in constrained environment, and we want to make it more robust. We want to increase the constraint, reduce the constraint, and make it safer. And our responsibility in academy is to make sure that we can communicate all the issue of robustness, address them, provide better evaluation, better models, and so on. And my last comment on this, that self-driving car, as a researcher, is an amazing application because it involves all the challenge. But for us researchers, what we're really interested in is the core challenge of modeling interaction, being able to do it. And self-driving car is one example. But we apply it to many other applications, like at city scale, understanding mobility for healthcare. So, yep. I don't know if I answered your question.
Last quick question, maybe.
Thanks. Do you think this kind of methodology would work well on social agents that normally we would consider as being kind of socially unpredictable, such as like children or animals?
Yeah, I mean, in fact, yes, we also use this to help autism, right? Kids with autism. And indeed, it's about understanding the intention, understanding what they want to do, being able to understand this cue, being able to do the diagnostic of autism. So it's the same technology.
So you would say that there's still some kind of underlying social rules, even if they seem kind of unpredictable to us, I guess.
Yes, absolutely, but maybe not even social, but maybe they have a body language that will allow us to better understand their disease and where they are in the disease, the state of the disease.
Okay, cool, thanks.
Okay, then one last question before lunch.
Yeah, sorry for lunch.
Hi. I guess we do have situation where the collision is actually inevitable. How do we prioritize?
Yeah, we also have we talk about it in class, the ethics of a self-driving car and how to make ethical decisions. It's a 2 hours discussion. I'm not going to, we can maybe do it offline or in a different talk, but at the end, we are trying to see if we can at least reproduce one ethic. It can come from the government, from your policymaker, or from the user going in the car. Suppose that the user said, this is my ethic. In all this critical event, I want the car to behave like this. Because we have free will. And this is what right now we're studying. How can we learn the ethic of someone in a very, very fast way, maybe a few questions, and make exactly the same ethical decisions in the critical event.
Thank you.